All right, energy. You've seen this? You saw it probably for the first time in Gen Chem 1. We're going to kind of revisit it. Every event in the universe involves energy in some way or another, either producing or utilizing. Living organisms have a large energy requirement. The sun and photosynthesis are great providers of that energy and processors of energy. Different forms of energy: gravitational, nuclear, radiant, heat, mechanical, electrical, chemical. Energy is the capacity to do work, and work is the organized molecular motion that uses force to move an object. Okay. Now, as it pertains to this class, one of the ways that you could think about this is with this flow chart right here. The sun produces energy in the form of light that photosynthetic organisms use to produce sugars and polysaccharides that organisms that consume leafy greens and sugars can convert into food energy. A first carnivore would be an organism that processes what that eats that herbivore. That first carnivore is then consumed by the second carnivore, which would be an example of fish. And then those who eat fish they're right there. So indirectly multiple times over, the sun, or light energy from the sun, goes to man. Energy in living systems. Large molecules become small molecules that release energy. This is a form of catabolism. Small molecules become large molecules that require energy, and this is a form of anabolism. These are our definitions that we actually talked about, I think, in chapter number 1. Catabolic processes versus anabolic processes. We talked about it breaking down versus building up. Well, you have that same sort of thing. Large molecules broken down and releases energy broken down from large molecule to small molecule and releases energy. A small molecule, energy is input to build up a large molecule. Energy regulation is an essential feature of cell survival. So storage of energy and conservation of that energy, rather than ingesting something and basically having to constantly feed in order to continue to exist. As glucose is burned, most energy in glucose is released as heat. Glucose is oxidized in several small steps. Now, the modern concept of energy is an invention of the Industrial Revolution. An investigation of energy transformations that accompany physical and chemical changes in matter have been used to evaluate the flow and interchanges of matter and energy. Now, our goal ultimately is to predict whether a reaction will occur spontaneously without inside or outside intervention or not. This is used to keep track of energy available to do work within a cell. So the laws of thermodynamics that are important for this course. The first law is the total amount of energy in the universe, is constant. Our enthalpy, our heat of a reaction, delta H, the change of heat in a reaction, is going to either be less than 0 or more than 0. If it is less than 0, that reaction releases heat. It is considered exothermic. If it is greater than 0, that reaction requires heat and therefore is endothermic. Now, the second law of thermodynamics. Disorder of the universe always is increasing. Entropy, or S, measures disorder of the system. So delta S is less than 0, meaning it is an ordered process, a process that produces more order than was previously present. If delta S is positive, that's a process that adds disorder. So that's a process that has gone from an ordered system to a disordered system. Now, if we look at this model right here, we've got two different things taking place. What I'd like you to do is look on the left-hand side of this image. What we have is a division between a system, an enclosed system indicated by this blue circle right here, and then the surroundings, which are separated from that blue circle, but is still kind of encapsulated. So these would be our surroundings, and this would be our system. Now, on the right-hand side, what we have is we have movement of these different objects. So free energy is the energy available for work. A more convenient thermodynamic function for predicting spontaneity of a process is derived from the delta S, the entropy change of the universe, is equal to the entropy change of the surroundings plus the entropy change of the system. Now, known as Gibbs free energy, delta G is equal to delta H, the heat exchange of a reaction, minus T delta S of the system. So what we really are curious about is what's the Gibbs free energy change of a reaction. Now, if that delta G is equal to 0, the reaction is at equilibrium. If the delta G is less than 1, energy is released. This is an exergonic process. This is exergonic and it is spontaneous. Now, if delta G is greater than 1, that means we have to input energy. This is an endergonic process and it is not spontaneous. Okay, so think about this as these values, so delta H and T delta S, combine to either make delta G less than 0 or more than 0. That's what matters at the end of the day. Now, one of the things that we commonly see in biochemistry is we see reactions that are coupled together. So reactions whose delta G naught is greater than 0 can be coupled to a reaction with a delta G that is less than 0. Well, the reason for that is, think about it as you have two different processes or two different steps in one process. The process is an overall favorable reaction, but the two individual steps, one might be very favorable and the other one might be very unfavorable. So the reactions are in a series and are overall additive, and therefore you can combine an unfavorable reaction with a favorable reaction. Now, an example of this is the interconversion from glucose 6-phosphate to fructose 6-phosphate. Now, you don't need to worry too much about the specifics of this. Just understand reaction 1 produces a product that is used in reaction number 2. Okay, so now this first step, what's our delta G? Well, it's a positive value, so that's an unfavorable reaction. Our next step, on the other hand, well, we're going from fructose 6-phosphate to get it phosphorylated, fructose 1,6-bisphosphate, to make ADP. That's an overall negative delta G, so that's a very favorable. So I'm going to be a big smiley face here and then frowny face there. So in combination, these two steps are overall favorable. So the net free energy of this is going to be negative 12.5. So when these two steps are right next to one another, this whole process is favorable. The individual steps differ in terms of their spontaneity and their favorability, but the combination of them make them overall favorable. Okay, adenosine triphosphate plays an extraordinary and important role in living systems. Now, it is a great molecule for the storage and transport of energy. Our structure of it looks like such. We've got 1, 2, 3 phosphate groups. We've got our ribose, and then we've got our adenine sugar right there, or our adenine nitrogenous base right there. Now, ATP hydrolysis immediately and directly provides free energy to drive an immense variety of endergonic biochemical reactions. Now, this ATP, we have that third phosphate group. Now, that third phosphate group likes to break off and be transferred to something else. So this is also known as phosphate group transfer, and the energy associated with that is also known as the phosphate group transfer potential. Now, energy released is coupled to energetically unfavored reactions. So what we have is a couple of different reactions. We've got phosphoenol pyruvate plus ADP yields pyruvate and ATP. Glucose can get phosphorylated because this is so the movement of a phosphate group onto this molecule is an overall favorable process. So both of these are favorable processes because that ATP, to illustrate the magnitude of this hydrolysis and the energy associated with this hydrolysis, we have ATP which is hydrolyzed, so ATP plus H2O yields ADP in PI. The delta G for that is negative 30.5 kilojoules per mole. Now, removal of 2 phosphate molecules and production of PPI, or inorganic pyrophosphate, well, the delta G for that is negative 32. Now, that PPI can subsequently be broken into 2 inorganic phosphate molecules with a delta G of negative 33.5. So we have this ATP hydrolysis, this breaking down from ATP to ADP and ATP to AMP and PPI, where we're breaking these phosphodiester bonds and we're producing a huge amount of energy that's released. So why is ATP hydrolysis so exergonic? Well, one factor is we have electrostatic repulsion that is going to be reduced. So ATP carries 3 or 4 negative charges, and those negative charges are all going to be on those phosphate ions. So if you think about what a phosphate group looks like, negative, negative, and then here's a P, negative. These two groups right here and right here, they're going to be repelling one another. And so when you break that bond, now they're no longer repelling. ATP products are resonance hybrids, in which case they're going to be stabilized. Or this should say ATP hydrolysis products. ATP produces, products more easily solvated than ATP. And what you've got there is increased disorder. Random movement of more molecules are in the aftermath. So if we look at a phosphate molecule, like I was saying about the negative charges. So here's one phosphate molecule. This is going to be resonance stabilized. So effectively, it's a, well, as we know about resonance structures, it's an average of all 4 of these different depictions. So that hydrogen is not assigned to any one of those 4 oxygens. Instead, it's going to be a part of the resonance stabilization. So ATP synthesis, hydrolysis is going to be favored, the synthesis is unfavored. So going in this direction from ADP plus PI yields ATP and H2O, well, that's going to be the exact opposite but the same magnitude. Rather than negative 30.5 kilojoules per mole, this is 30.5 kilojoules per mole. Now, hydrolysis of other molecules that release more energy is coupled to ATP synthesis. Okay, so most of this material we're going to be revisiting whenever we talk about specific enzymatic reactions, because I think that this has its most context, or has the greatest amount of context, whenever you look at it when you look at it as a part of a metabolic pathway. And so we'll be doing that down the line. But just go back and make sure that you understand the fundamentals of, delta G, negative or positive. Is that a favorable or unfavorable reaction? Order or disorder, is that favorable or unfavorable? And, is heat required in order for a reaction to take place? All right, well, I hope this is helpful, and I'll see you in the next chapter.